after lunch, what could be more palatable than Bayesian statistics? Simple has an asterisk next to it. You'll find out why. My name is Jeff, and I am here to entertain and enthuse you, I hope, about Bayesian statistics. I have several declarations. I'm very happy to be here. I've been at many of them. I don't know much about Bayesian statistics, but I'm slowly improving. Many of the Bayesian designs that we want to know about share a particularly simple probability structure, and that's an emphasis today. And that combines the prior information with the evidence that we have in front of us from our trial, the data to hand. But you already know that Bayesian research models are often not simple. I nevertheless want to talk about two statistical vehicles to get us down the road. And obviously there are three important journals, the only ones we need to publish in. The New England Journal, the JAMA, and Critical Care and Resuscitation. We have editors from all three in the room. What's the prior probability of that happening? On my left, on your left, is the vehicle, the statistical vehicle B for Bayesian. Using the mechanical structures of it, we look at the blue curve, which is the data to hand, the likelihood methodology, and we combine it with the red curve, which in this case is a reasonably strong but moderately pessimistic prior. We put those two together and we analyse our result. On the right-hand side is the time-honoured and somewhat simpler in that we understand it and we've learnt it over many years, frequentist approach that only deals with the data that we've generated to maximise the likelihood in many cases and give us the answer from our trial. Both are very fit vehicles. Both work extremely well to get us where we need to go. My point today is we need to learn to drive the Bayesian vehicle a bit more. Now, this is going to be a talk that will be beneficial for everyone in the room. Because the people who have read that book and understand why gamma and likelihood are in the middle of that slide and have read the Bayesian guidance for devices and have been following the literature for perhaps several decades now, they can use this next half hour to check their email and perhaps send some SMSs to friends. So that'll be useful to them. For the middle ground, who've been reading the only journals that matter, including JAMA, they've been helped following for many years now, introductions, guides, things that make it easy for us to understand. And so they'll understand most of what's going on and they might sit back, have a daydream, or perhaps, just get reminded of certain things. There's just a huge amount of literature out there on Bayesian designs and how to interpret them. There's also the group of people who have seen with great envy these Bayesian reanalyses of frequentist data and said, wouldn't it be nice if I knew how to do that and how to interpret that? And it's for you that I'm speaking. This is the only thing that matters. If you want to take nothing else from this lecture, then take away that the posterior probability distribution is proportional to the likelihood probability distribution, that is describing the data, and the prior probability distribution that you bring from your prior knowledge. You must have a prior to get a posterior in a Bayesian analysis. Even if that prior adds nothing to the analysis, it must be there. And we'll see some examples of that. So that's Bayes' rules simplified. Here it is, not so simple. On the left is the posterior probability. We have the likelihood, the probability of the data given the parameter of interest or parameters of interest. We have the prior probability, and underneath that fraction in the denominator is something that's got an integral in it and is very complex and indeed impossible to analyse very quickly in anything more than the most simple of Bayesian analyses. And so there has to be a way to get around that. And many, many years ago, a way was found. We'll talk about that. And that way is that if we can't integrate the Bayes to make the probability proportional from posterior to prior and likelihood, well, then we simulate it with this fancy acronym MCMC, which gives us a shape of the posterior, even if we can't calculate it. Now, we're not going to do much of that, except in about 15 minutes' time, you'll just have a quick glimpse of what that looks like. But let's start with something really simple, a Bayes rule simplified. We want to find a posterior probability distribution from our trial. We want to get the answer, and we would like to consider the likelihood distribution of our data, and we're going to come with some priors. So we're just going to work through a couple of examples here, and we're going to use the simplest of Bayesian designs where you can actually calculate the posterior. You don't have to simulate it. The structure of the data models in likelihood and prior is set to very convenient probability distributions. You can actually multiply together and get the answer. You can calculate it. So we're going to do one of those in a second. We're going to use a proportion outcome, a mortality outcome, the probability of death in two groups. That's a proportion. That is described in terms of a binomial probability density function. We're going to use a beta prior, beta distributed prior, because that happens to be what is called conjugate, in that if you multiply a beta with a binomial, you end up with another beta, and the beta gives us an answer straight away. We understand what that is. So we can calculate our posterior probability of mortality benefit or worsening in an example that we're about to start. There are a number of other conjugate Bayesian families. Gamma with Poisson being a count distribution will give us a gamma again. The simplest of gammas is an exponential function. We could also have a normal prior with a normal data structure, pop that together and end up with a normal prior, a posterior as well. But we'll start with the top one, which is the easiest to show you a binary outcome, survival or not, something that we're very familiar with. And so a beta binomial model might sound so simple as to be not publishable, and indeed we'll show an example where beta binomial is published. So let's go to the only other journal that matters apart from critical care and resuscitation. And I was casting around for some binary outcomes that had some posterior data attached to it. And what did I find? ECMO. So in no way am I commenting on ECMO. I want you to remember that when you start shouting at me in the next few slides. But here we are, January 26, a trial of ECMO. And I'm going to focus on the primary outcome, which is an odds ratio 1.4 in terms of survival in favour of ECMO CPR. Okay, the underlying design doesn't matter. What we have here is 14 out of 70 people surviving with the intervention, and we have 10 out of 62 surviving with the control group. And so we have a binomial description, an odds ratio, and a confidence interval. That's the frequentist approach. By the way, those of you that are quickly calculating, can you tell me where that risk ratio comes from? Because I'm not sure. It looks too small to me. So we won't worry about that. Remember, the posterior, the result we want, the posterior probability density function is proportional to the likelihood, which is binomial here, and the prior, which we've said is beta, to make things work. So this, we just take a second. We're going to show you a few of these kinds of graphs. Along the bottom, the x-axis, it goes from 0 to 100%, from 0 to 1. That's a probability range. You'll recognize that as the entire truth of probability. You cannot have a probability less than never or more than always. So that's the probability range. There are three curves on this. The blue one is hidden behind the green one, and we'll start with the yellow one. The yellow one is saying, I have no idea whether ECMO control, sorry, this is the control group, whether it works or not. I have no idea. Now that is a very non-informative, very flat prior. Can you see that that's a beta 1-1? It can be specified a number of different ways. Think of it as, I've seen one success and one failure. I have no idea whether it works or not. That's sort of what the beta 1-1 means. So that's our prior, and it's a non-informative prior. We put that together with the observation in the control group of that study from New England Journal in January that there were 10 survivors in 64. Some of you are awake will remember that I said 10 out of 62. The abstract actually says 10 out of 64. The detail said 10 out of 62. I discovered that this morning. Bad luck. I'm not recalculating it all for you. So one or the other, it's close. One's 15.6% as I've got here. The other one's 16.1%. So survival in the control group was observed to be around 16%. That is our likelihood, our binomial likelihood. That's sitting exactly behind the posterior result, the probability distribution of seeing 10 survivors out of 64 is that green curve. Can you see its average is 16.7%? Can you see it's jumped up very slightly from the binomial likelihood, the one that you as a frequentist would report to me, because we've actually put in one person who survived and one who didn't in the prior. So it moves it a little bit. If you really got upset about that, you could specify a beta with a number less than 1 into it, such that essentially it says nobody has been seen. But it makes no difference. So that's our prior probability with a binomial likelihood in the control group. That's what we think a posterior is in the control group, expected around 16.7. Nothing too thrilling there, but did you see, I'll do it again here, watch the green curve jump. We're now in the ECMO group, and this is what we observed. We observed that 14 survivors out of 70 people in the intervention arm with ECMO. We've come in again into this Bayesian, simple Bayesian beta binomial model here. We have our non-informative prior, beta 1,1, which is that yellow flat distribution. We have no idea. We then come along and see 14 survivors out of 70. That's a blue curve hidden exactly behind the green curve, which is our final answer. Putting the beta with the binomial, we get that posterior probability of a beta of 1557, in other words, a mean of about 20.8. So that is incredibly similar to the binomial likelihood that a frequentist would report to us, because it must be. We've not given any new information. Our non-informative prior means that, in fact, both the Bayesian analysis and the frequentist analysis have only got the data to work with, and they'll return essentially the same order of magnitude of estimate. We take those two away to get the difference. So I've just zeroed in on those two posteriors, one at about 16%, one at about 20%, and you can see that the grey curve has now appeared. It's the difference between those two posterior estimates, one for intervention, one for control, and we're going to zoom in on that grey curve now. And that grey curve has a series of vertical dotted lines attached to it. The one to the left is 0, the other is a little to the right of 0. And let's start with a summary. The mean risk difference, which comes out of a 2x2 table that any frequentist software will give you, was 4%. Between 16% and 20%, of course it's 4%. The 95% frequentist confidence interval was somewhere between 9% worse to 17% better. And because we gave a prior that had essentially no contribution of knowledge, the posterior estimate from this very simple model is reassuringly the same as numerically the same as the statistic that you're so comfortable with. It can't be otherwise. Really, it's going to be very close to that because you're using the same data. So that's the reassurance as you jump from frequentist to Bayesian, that Bayesian is not magic, it's working on probabilities. It's a clever way of applying conditional probabilities. But let's go much further. That frequentist statement, 0.04 with a confidence interval of 0.09, one way to 17% the other, can be much more richly given to you in Bayesian analyses as follows. So we have a posterior probability of 26% that the ECMO is worse, and we have a posterior probability of 73.8% that ECMO is better. And if I say, no, but I wanted at least 1% absolute better in terms of survival, we'll have a posterior probability of 68.6%. And if I say it must be at least 2% better, then I have a posterior probability of 63% that is the case. And can you see that all the way down to a posterior probability of only 0.008 that it's 20% or more better? So same data, but for me, a useful, richer way to describe what we have. And that is one of the reasons I'm advocating that we spend a little more time asking whether we should be designing some more of our studies to have this kind of Bayesian probability statement rather than a point estimate and a confidence interval. Now, to remind you, every time you see this, we're changing to some new data. We're still in the beta binomial, simplest of the conjugate Bayesian analyses, and we're coming in with a prior. But this time, the prior is informative. It's got information in it. We know something, and we are going to include this information in our analysis of the same data that's in the January 2023 New England Journal ECMO study. So we're now bringing other ECMO or data that I say is relevant. Now, whether I'm allowed to say that or not doesn't matter. I'm telling you it's relevant. It's coming in for the purposes of today. And here's the relevant one. This one is Lancet 2020, one of those journals that I didn't list, but I suppose we can accept if we couldn't get into critical care resuscitation, New England Journal or JAMA, we might accept Lancet, I suppose, as a fourth option. So here we are, informative prior for ECMO, and here it is. And look, it's a beta binomial model reported in that study. Isn't that reassuring? So a couple of years ago, this study stopped at around 30 people because it found that out of 14 people on ECMO, 6 survived, 8 didn't. Whereas in the people who were not on ECMO, 1 survived and 14 didn't. And so they were so convinced that they felt they needed to stop that study. So that's a very enthusiastic prior, even though it's a small study. So keep in mind, small study, but enthusiastic prior. What does it do to the New England Journal data that we've already analysed with our non-informative prior? Well, here's the control group, and you'll remember only 1 out of 15, 1 out of 14, 1 out of 15, 1 survivor, 14 died in the control group. Can you see the prior is now, the yellow curve is very much bunched up down to the, we don't think this works. Very low probability that it works. Can you see that there? That's the beta 114 shape. We add that to the binomial likelihood of the control group, 10 survivors out of 64 from the New England Journal, and we end up with the posterior probability, which is the green curve now, estimating about a 13.9% mean difference, a mean effect. Can you see that always the posterior is between the prior and the likelihood? It's a kind of a weighted average. That's the beauty of a Bayesian analysis. Now, here we go with the enthusiastic data from the Lancet added to the New England Journal data. And this is in the ECMO group. And you'll see that big yellow curve there is the enthusiastic prior that we get from seeing 6 survivors out of 14 people. Only 8 died, 6 survived. So that brings us up to nearly 50% average effect of this being good. And we add that relatively small, but now very enthusiastic prior to our other data. And you can see where the posterior is, and it's sitting at 23.8%. It's moved up a little bit because of that enthusiastic prior. And we take the 2 away and we get to this grey curve, and we'll jump into that grey curve and the posterior median probability that ECMO works if I combine New England Journal data with what I am saying to you is entirely compatible prior data from the Lancet 3 years earlier, increases my overall posterior median probability. And now I'm pretty comfortable that I've got a 94.9% chance of ECMO being superior. And if I ask for it to be at least 10 points superior, I've got a 49.2% probability. So again, I can more richly describe for you what the level of evidence is across this probability distribution, because we're being honest for the first time. When we gave point estimates in frequentist analyses, we often didn't consider the variability of that data particularly. Here it's explicit and in front of you. So here we are now with a different prior. This will be the last one. This is another ECMO study, surprise, surprise. This is in JAMA, a really good journal. And here it is, reported in more of a frequentist way. It was stopped, this one. The P of 0.09, one of the things that we've discussed this morning, how tantalizingly annoying to stop a study with a P of 0.09, say that it's futile. Odds ratio 1.63 in favour of ECMO, confidence interval just under 1, all the way up to 2.85. And we see that we have 39 survivors out of 124 who got the aggressive strategy, and we've got 29 survivors out of 132 who got the standard management. Can you see that's a much bigger prior, but it is not quite as enthusiastic. What does it do? Well, here it is. Here's the control group with the less than enthusiastic prior, but now very clearly a tall peaked curve, very sure of where it sits. No great uncertainty about where the prior is now, and we put that together with the data that we've seen now twice before, and we get a posterior probability of nearly 20% in the control group for survival. And here we are with the active arm, the ECMO arm, where we saw 31% survival, and a posterior has moved up to 27. We take the two away, and now we are moved again further up in favour of ECMO, that our median posterior probability that ECMO works, combining that bigger prior with the New England Journal data most recently, is it's 7% better, and it's almost 95% credible interval, a Bayesian interval, almost not including any possibility of harm in the 95%. And if we wanted any other percentages, they're there on the graph, so that we, for example, are 89.7%, essentially 90% sure that it's at least 5% better. I find that more useful to describe the conundrum of where we are. Uh-oh. So this is that horrible thing. And remember, it's an integral at the denominator of this crazy function, and you can't work it out. And so you have to get around that. And many clever people in the last 70 or 80 years, but particularly in the last 40 and 30 years, have got to the stage where Markov chain Monte Carlo methods are a simulation of a posterior distribution that we don't know and can't calculate. But through the magic of that mathematics, it figures it out for us. So you don't have to do any fancy integrals. You can't calculate with a formula the result like I just have in those beta binomial conjugate models, but you simulate the posterior distribution and that gets you answer. That's where it costs the time. And you've heard people grumble about Bayesian analyses being requiring a lot of effort. That's where it comes from. And so in conclusion, that effort comes now because somebody, either you or the biostatistician you're employing, has to use fancy software that they may not have used before. Stan was Stanislav Ulam. He was a nuclear physicist and a mathematician, and they were working on the atomic bomb. And they had to simulate posterior distributions of, I understand, neutron activity. So in honour of Stan, people have decided that the software that does Bayesian analyses and does these Monte Carlo Markov chain simulations we call Stan. Of course, it's free, and so you can download that today. I recommend you all rush out and do that. Stan interfaces, as you can see, with R, which is a free statistical environment that you've all heard of, and it's taken the world by storm. There's other environments. Wouldn't you like to work with Python, MATLAB, Julia, and Stata? And so Stan exists. R is pretty much where this cutting edge software is being released, and there's an R Stan. So those who can use R can work in a more comfortable context of their coding and get into Stan. And dummies like me might be able to be this. The primary target audience is people who would be open to Bayesian inference if using Bayesian software were easier. But otherwise, I'll use my familiar frequentist, please. So RStanArm, which stands for using R to access Stan and doing applied regression models, is the next thing on the block. There are multiple different ways to do this, but that's one that I recommend you ask your biostatistician if they can use. Now, you could also use Stata, which is wonderful, but not free. And that's a partial list of all the built-in Bayesian analyses that it supports. And there's other Bayesian analyses built into lots of other programs. So there's a huge wealth of support if only we could understand what to do. And there are some people in the room, and you know who they are, who are checking their emails right now because they know how to do this. But the rest of us need to ask them in perhaps, I hope, a more informed way. Maybe we could do a Bayesian analysis. Can you do this for us? So there's the study. And I can't really simulate that data. Remember, it's 132 people, and there's two groups, 70 and 62. I tried because I wanted to run it in RStan to show you how good I was. Well, I got as far as my posterior median odds ratio was 1.38, but I got the variance wrong. So my credible interval was a bit too tight. But nevertheless, this is how it's done. And I highlighted in green what your biostatistician is looking in the distance with vague sort of eyes as you talk to them. They're trying to imagine the rubbish you're telling them in code. And so here's a tiny bit of an insight to what that poor statistician has to do. They have to open an RStan arm. They have ECMO model prior. They are going to RStan generalized linear model program to do it. Why is the outcome? Did you survive or not? And the only thing that explains it is ECMO. I've only got one variable in this data set. The data was JP simulated. The family is binomial. The prior for the intercept, the beta naught in this linear model, and the prior for the beta 1. And they don't look anything like what you told them, and that's because they're on a log odds scale. Can you see that there? Minus 1.66 and a 0.27, because we're working with log odds in logistic models. It then, if you get it right, press go, it runs off and runs chains for you. And we've said, could you give me 4 chains of each 10,000 and throw away the first 5,000? So we ended up with 20,000 20,000 simulations from the prior of possible intercept and slopes in your model. And then at the end, we update it and ask for the answer. That's a visual description of what's happening. Down on the bottom on the X curve, there's 0 and 1. On the left is you didn't get ECMO. And on the y-axis is you survived. And keep in mind, this is binary with just 2 groups. So you either survived or you didn't. If you survive, you're in the top group. If you didn't, you're in the bottom group according to your treatments along the x-axis. Can you see in the right top corner, there's more survivors in those who got ECMO than those who didn't. So the blue top square is showing more dots than the black top square. So that is a visualization of what the 20,000 simulations is all about as it runs off doing its Monte Carlo Markov chain magic. We've pressed up instead of down, I'm sorry. And so that is the end of the talk. I think we should use either Bayesian or frequentist analyses. We are very familiar with frequentist. We need to learn more about Bayesian. It's a very fit vehicle, and indeed it has some advantages. In a way, it might be a bit of a sports car for some of the things we need to do when we're lumbering along with the truck of frequentist analyses. But we get there with either, and we've certainly had great success with driving the frequentist bus. But I think we need to get on the Bayesian sports car soon. Keep that in mind as the only thing you need to take away from this. If you want to borrow my copy of Bayes' Rules, I haven't finished it yet. It's 500 pages and it's a great read. Thanks.
Yeah, it's always a pleasure, and great to hear you try and make that understandable. I'm sure there are questions. Any questions? Yeah. Emily, Kathy, and Ian.
Thanks, Jeff, for a really comprehensive but easy to access summary of Bayesian analyses. My question is, if you've got multiple previous trials that you can use to inform your prior, can the software accommodate that easily? And what if the study populations are slightly different to the trial that you're intending to do?
Thanks, Emily. Great questions. Now, that's the art of statistics rather than the science. So the whole question of whether you're allowed to bring prior knowledge to what you hope is going to be highly unbiased scientific conclusions is the whole issue. The whole, one of the major controversies in the past about Bayesian analyses is the alleged subjectivity of the bringing of a prior knowledge, and particularly if that knowledge is informative, how your conclusion inevitably changes. And indeed, it's the magic of Bayesian analyses that the prior knowledge is integrated with the current knowledge. But in fact, two things to be said. We shouldn't be frightened of that if we follow correct rules. The second thing is it's the way we think. So all of us do not interpret the data in front of us in a vacuum. And so it is very acceptable, and I think probably relevant that we start moving in the direction of considerations of Bayesian analysis. But it's still very much the case that non-informative or minimally informative priors are currently the fashion, and that's fine. That's fine. But the business of combining prior